5, and we're going to use practice problem here on page 97 about permanganate and oxalic acid. So we're going to talk about redox reactions and organic, and then anything else that they decide they want to talk about. Okay, so this problem here says dilute potassium permanganate solution is added to an oxalic acid solution that's acidified with sulfuric acid. So I like that question because it puts sulfuric acid in the question. And one thing a lot of people want to do is put sulfuric acid in the formula, the equation, and we don't want to do that. You guys can? Okay. So the reason they say that is just telling you that this is an acidic solution, and then since it's an acidic solution, that's a reminder that we've got hydrogen ions we can use to balance this when we need to. So when we go to write it, we don't care about potassium because we know that it's going to be a spectator. So I'm going to put in permanganate, and then oxalic acid is one of those polyatomic ions that you're probably not very familiar with, but it is a good one to know. I think it's a -2. And then these, the more you can remember about what they become during an oxidation reaction, the better your life's going to be. And in this one, permanganate is going to turn in just a simple manganese ion. And remember, the manganese ones and the chromate ones are the ones I said are most important to know because those almost always come up on the AP test when they're talking about redox. So you're going to have something that has oxygen with it, and you pull those oxygens off, and you're going to be left with your ion. And the manganese has a +2, and the chromate has a +3. That's the most common thing you're going to see. There are tons of other possibilities, but those are the most common. And then in this instance, the oxalate ion turns into CO2 and H2O, but I'm going to leave the H2 off for now. And I also left the H+ off on this side because we'll add those back in as we balance it out. Questions so far?
Is it chromate or dichromate?
So chromate and dichromate are both possible situations. Dichromate comes up more often than chromate, but I would suggest knowing both.
Chromate is the
Any other questions? So first step when you're balancing a redox reaction, identifying that it is a redox reaction is good. One of the things that I do want to mention is I think the likelihood is that they'll give you the equations. Even the more recent FRQs before they changed into the new test, they were giving the equations for these, and your job was to balance them. So I think that's what you should make sure you're really good at. But in case it came up and you had to identify with the products, I like you to know that. So when I separate it into the two halves, I'm going to put the ions that go together. We know permanganate becomes the manganese ion, and oxalate becomes CO2. And so now I have two half reactions. And the first thing that's most important is that within that, any compounds that aren't oxygen or hydrogen are balanced. Not compounds, excuse me, any atoms. So for example, if you had multiple manganese, you'd want to make sure you have multiple manganese. You don't, there's one on each side. But notice you've got 2 carbons here, but it only made 1 carbon there. It's probably bad. So I'm going to go ahead and put a 2 here in front. That doubles my carbon. Happens to balance out my oxygen, so that's great, but we're not really worried about that. So we're not going to care that there's no oxygen balance here. We'll take care of that later. So oxygen and hydrogen we worry about last. In this 5 steps to 5, they do go ahead and next balance oxygen and the hydrogens. I like to balance the electrons first. So I'm going to do that. It's a little different than the way they describe it. Both ways are fine. I think if you balance the electrons, then that's going to account for your numbers better than if you balance oxygen. So that's just me. So what's manganese's oxidation state? Do you guys want me to go back over that? +7. So -2 for the oxygen. There's 4 of them. So that's -8. And so you're -8, that means manganese has to be a +7. So to go from +7 to +2, what did it do? So it gained which electrons, which remember is reduction, and 5 of them were gained. So then the carbon atom, each carbon atom, well, we should figure out what its oxidation state is. So -2 plus 8. So overall is a +6 for the carbon set, and there's 2 of them. So each one is a +3. I don't know why I keep. All right, so it's a +3, and then I moved it over to here. It has a neutral charge because it's just CO2. So when I have a -4 charge on my oxygen side, that means I have to have a +4 on my carbon side. So if I go from a +3 to a +4, what had to happen? Good. So remember, Leo reminds me that losing electrons is oxidation, and we lost 1 electron. However, we have 2 carbons. So each carbon lost an electron. So I'm going to multiply this by how many carbons I have. So we went 1 electron times 2 carbons means I'm transferring 2 electrons total. Does that make sense? And we can't lose 5, or I'm sorry, we can't gain 5 on one side, but only lose 2 on the other, because remember, these are accounting for the same set of electrons. So this is where we'd want to balance our number of electrons. So we'll double this side so that we're actually moving 10 electrons. We're going to multiply this side times 5.
Those students that are here for the mentor meeting, that meeting is being held in the PAC this morning, starting at 7:20.
So then, now when I balance that, my electrons match. And so I'm transferring 10 electrons. And if I were to see this on a multiple choice type question, I think that's the question they would ask, is total number of electrons transferred, potentially which one's getting oxidized or which one's getting reduced. Those are the type of multiple choice questions that I'm gonna expect you to see. So anyway, then we're gonna keep going. So I'm gonna rewrite it down here just because I kind of don't have very much room. So now that we've established how many we need of everything, the last step before we squish them together is to make sure our oxygens and any possible hydrogens are balanced. So on this side, notice I have 8 oxygens on the left, but then nothing on the right. So since this is all happening in solution, that means we have water, and we know water has oxygen in it. So we're going to add water molecules. We're going to add as many water molecules as we need to get to match our oxygens. So since each water molecule has 1 oxygen and I need 8, I'm going to add on 8 water molecules. And of course, I can't also just add hydrogen without any other hydrogen. So because here I added 8, each water molecule has 2 hydrogens. So I'm going to add 16 hydrogens here on the left. It's in an acidic solution, so we're good with having extra hydrogens. That's no problem. Questions on what I did there? Okay. So then I need to balance my oxygens. It gets a little trickier here because I have oxygens in both compounds. So we do want to make sure we account for that. But I've got 5 times 4 oxygens here, so that gives me 20. And 10 times 2 oxygens here, so that gives me 20. It's not that much trickier because it's already balanced. Then the fun part is just putting it all together. Sometimes you would get it so you have waters and hydrogens here. They're going to end up being on the opposite side, so you would want to check to see if any of them cancel out. They don't happen to here. So now I'm just going to put all my reactants together. And then if you happen to see in the 5 steps 2-5, notice we ended up with hydrogens and water back on the correct side that the book had put them in. So I would see on the AP test, they probably would have given you this equation and they probably would have gone ahead and put hydrogens on this side and H2Os on this side, and your job would be to balance it with the right coefficients. And so if you just leave them off when you go to write them out, and then that's one really great way to check your work, to see, hey, my hydrogens ended up on the right side, so I'm probably correct on that. Another thing I would encourage you to do is check your charge balance. You guys know how to check your atom balance because that's what you've done since general chem. But checking your charge balance is going through and making sure that whatever the total charge is on the left has to match the total charge on the right. So like here, we've got 16 positives, 2 negatives, and oh, did I drop a charge here? Oops. I dropped it here. All right, you guys should stop me when I start dropping my charges. And then 5 times the negative 2 gives me a negative 10. So that gives me positive 16 plus the negative 12. So I get a positive 4 on the left side. And then on my product side, I've got 2 times plus 2, so I got plus 4. Water has no charge, and carbon dioxide has no charge. So this side also has a plus 4. That means I probably balanced it correctly. You're unlikely to get to have charges match up like that unless you had correctly balanced it. And then, of course, you do want to check your atom balance and make sure those work. So all of those things are great ways to check your answers. And this is just side note. This unit we're on with acids and bases, a great tool to use when you're trying to figure out that moving of the hydrogens or the hydroxides that can help you kind of see, did you do it the right way? Did you add the charges the way you're supposed to if you end up with the right charge balance? So that's good all the time. Yes, ma'am.
I wanted to know H2O on the 604.
Here, why didn't I put H2O in? Because I didn't put H2O here because my oxygen's already balanced. I had 20 oxygens on the left and 20 oxygens on the right, so we didn't need to. But had that not balanced, I would have added water in. Any other questions?
How would this work if there were a basic solution instead of the acidic solution?
And so the only thing that's different, if it happened to be basic, and I don't think that they'll give you those, but if it were, since a basic solution can't have hydrogens floating around, what you would do is anywhere where you added hydrogens, you would add the same amount of hydroxides. And so I'd add 16 hydroxides here, and you can't do one to one side without doing it to the other. So I'd also add 16 hydroxides here. These are going to form water. So that ends up with 16 water molecules. So my 16 here canceled my 8 here. And now it becomes 8 overall water molecules.
All right.
That's what would happen had this been a basic solution. I guess I'm going to erase all of this in a second. So that's a good question. Anything else redox? So like I said, this sheet with the strong oxidizers is a good tool to use. Strong oxidizers. Sleep with it. Set it next to your head. Look at it every morning. Okay, then we will talk about organic. So the 2 organic functional groups I see the most on the test are the alcohols and the carboxylic acids. Last night we did an alcohol naming one. And so today I was going to do a carboxylic acid. We kind of talked a little bit about carboxylic acids, so we'll talk a little about alcohols also. One thing I do want to say again, I have seen the most on the tests, what they've done is give you all the information. Maybe compare 2 compounds. They'll tell you their names, they'll give you some properties, and then they'll ask you to talk about them. Maybe they'll ask you an intermolecular forces question, like which one's going to have the stronger bonds. The last test they did, which one's going to be more dense. And so you had to look at the masses that are inside both of them and kind of compare the 2. So those are the types of things where you'll have all the information you need. You just have to be comfortable with it and then be able to apply it in some different way. But we'll talk about intermolecular forces in a couple sessions. So let's see. So a reminder, carbon always has to have 4 bonds. So when we're going through, I decided how many carbons I wanted to have, and then I added this group here on the end. This is a group over here that is my carboxylic acid. And notice it's called an acid, and that's not just for fun. It actually is an acid. It makes a low pH. It behaves just like all things that are acids. Notice it has this hydrogen right here, and that hydrogen is really easy to detach and go and react with something and go be an acid. So oftentimes you'll see that. In fact, we've used it a bunch because this can be part of acetate. C2H3O2, remember, a lot of times we'll write it like that. That's our acetate ion. And we can add a hydrogen on here, and that makes it acetic acid. That's the carboxylic acid version. And so we would put it like this. And so notice there's your carboxylic acid, and then the rest of it would be filled with hydrogens. So that's why I think they talk about carboxylic acid so much. It's really easy because it is also an acid. So you can focus on the acid base unit while you're talking about it. So anyway, we're going to go back to naming because that's really what we're here for. So you got to remember the prefixes. Remember that this time the number one is meth. Meth and eth are the ones that are most typically trick people, I suppose, because you always want it to be mono and di or bi or something like that. But 1 is meth and 2 is eth. 3 is prop. 4 is bute. 5 is pent. And then hept. Oops, I skipped 6. Hexa. 8 is oct. 9 is non. And 10 is dec. So in this instance, what are we using?
3 or 4?
Actually 4, because you do include the carbon that's in your carboxylic acid. But that's a great question, because everybody forgets that. So I have 4 carbons, so I'm going to use my bute. And then because it's carboxylic acid, that's our parent. That's going to be the one that's most important thing that is in my organic compound here. That carbon that's attached to it has to become my first carbon. So that's identified. You don't have to even think about it, which is nice. And carboxylic acids by nature have to come at the end. I mean, the functional group does. And so you would potentially have one on both sides, but you'll never have more than that. So if I happen to have also drawn one there, then you would decide your numbering based on, like this double bond here would have probably made this side become number 1. If there's another thing that goes with it. Do remember, if you had 2, you would have to use that prefix di. So you would say dioic acid. But because we have this double bond, any double bonds at all cause us to use a different suffix. So instead of the ane that goes with most of our organic compounds, we're going to use an en to represent that we have a double bond in there. If it had a triple bond, we'd use yn. If it had both, we use both. And you have to tell the world where that double bond is located. So since it becomes between the second and the third carbon, you always go with the smaller of the 2 numbers. So we'd say bute 2n. My preference is to put it in the number, in the word, but you could have put it in front as well. And then I'm going to go ahead and add my ending. You don't have to say where it is because there's just one, so everybody knows it's at the end. So you would say butanoic acid. And of course, can't forget the chlorine. That's an important one too, but we would just add it to the front end of it as kind of a prefix. So each of our halides, remember the ones in group 7, are often just added to organic compounds. And so they take their root and then end in O. So this is chlorine, so I'm going to call it chloro. And we would say where it's located, and it's on the 3rd carbon. So 3-chloro-2-butanoic acid. Sorry, I was thinking about alcohols. So questions on that? No? Good. Okay. Remember alcohols, like I said, I talked about them briefly, have the OH, that hydroxide group attached to it. And so you often will see multiple alcohols on there. And so each one of those would be a group. So this instance, my ending, instead of being oic acid, your ending becomes all, and there's 3 of them. So you do triol, and then you'd also say where they're located and how many carbons, and do all the same stuff as the other one. Alcohols tend to be flammable, have lower melting points, do things like that. And so they also often have can be used, I was going to say a scent, but that's not true. That's a lie. So once again, I don't think you need to know their properties by any means, but I want you to be comfortable when the AP test tells you things like, this is what's going on, and you can make decisions.
So would that be Prop 1, 2, 3 trial?
Well, you have to say the numbers because there's no ambiguity.
You would have to say numbers because it's possible that maybe all of the hydroxides were on 1 carbon. You'd still want to say which ones they were on. But yes, I would agree. This one would be 1, 2, 3, prop, N, triol. And same deal as last time, you could have also put the numbers within the name if you wanted to.
If all the hydroxides were on one, you would say like 3, 3, 3.
Yes, you'd have to say all of the 3s. If they were all in 1, then it'd be 1, 1, 1. But yes. So that's just a quick reminder on naming things. Do you have more specific questions about naming? So I said we'd go 30, 40 minutes. It's been a little about 30, so I'm happy to answer another question. If you guys have more, if you want to call it a day, I'm happy to do that.
Can you just really quick cover like equilibrium constants? So there's like a few of them, and I always get them mixed up.
Sure. This unit we're going to come back to equilibrium in a future review session, but I'm happy to talk about equilibrium constants now. Do you want to go over just like all of the ones we've talked about?
Yeah, like KSP.
So we've got just KEQ, kind of the umbrella over everything. All things can be KEQ. Then we have KC, which would be devoted strictly to concentration. These are often used interchangeably because this is kind of the basic K1. And then we can have KP, which is going to be devoted to pressure. So you have to be in a pressure unit. Most often you're in ATM. So this is usually we're using molarity. Typically we're using ATM. It could be KPA, but most of the time AP chooses ATM. KSP, this is going to deal with solubility. So while it's also molarity, the difference between these two is you're going to have a solid that's turning into ions. And then there's a lot of possible constants, like we talked about KD, which is sort of a combination of those two where you're looking at solubility. Bless you. But the reactant isn't a solid. There are other, like it could be an ion or something else that's able to separate out. So it kind of behaves like KSP, but you have to include the reactant. So just be prepared if other things come up, but they would choose that one knowing people haven't talked about it. So if they pick a K value you haven't talked about, they just want you to see what you can come up with. KW is a constant, and so it's based on the idea that your Ka times your Kb. So we would use it in our acid-base reactions only, and that Kw is 1 times 10 to the negative 14th. And then we have our Ka and our Kb values. So this is the one devoted to acids. Bless you. And this is the one devoted to bases. And they're both going to be in molarity as well. But these two, those are the ones where you have to make a choice on which ones you're using. So you want to make sure you're paying really close attention to your equilibrium expression. Trying to think about. And so Ka would be associated with an H plus or an H3O plus in your equilibrium expression, whereas Kb would be associated with a hydroxide.
So Kb and Ka are just the Kc of these different
Right.
acid-base association reactions.
Yeah, you're exactly right. And so Kb would need to have an OH in it. Those are the most common K values that we're going to use. Is that what you were going for?
Just,
There's a lot of them. It's a good thing to think about. Anything else?
Can you talk about the like, I don't know if you're calling the, I think it was the graphs of maybe the kinetic energy or something. I have kind of a picture of one right here.
What page is? Oh, that's just one of yours.
Yeah, it's like the prompt, I don't know if it's, I think we did some like this where.
Oh,
Yeah.
Boltzmann.
Yeah.
So just in general, like.
Well, then we talked about this at some point.
Yeah, we were just talking about them, like thinking about how you'd be able to, how the distribution changes based on what you do.
Yeah.
So speed's on the bottom, right?
Yeah.
So the question that we're talking about is, we're just reviewing what a Boltzmann distribution curve happens to be. And then on the side is probability of finding an atom.
Looks like a histogram.
Yeah, I would say that's probably a good correlation to this.
Okay. Because this is like a probability distribution. So, okay.
It's not necessarily what I would. So, like if you had your normal distribution, the majority of your molecules are going to fall in this speed right here, right? But you could find them other places. And so depending on what you do, you're going to adjust that. So if you lower the temperature, you might expand where you're going to find those molecules. But the total area under your curve should remain constant, because you're not going to like lose molecules. You're just going to change where they're distributed.
So the area is always going to be 1 under it, because there's always a 100% chance of finding a molecule.
Right, under your curve. And so
You don't
what
know
your
where-
picture there represented, I think, was changing the temperature.
Yeah.
So if you lower the temperature, which is the most common way of doing it, because when you increase the temperature, it's kind of harder to think about. Now you're going to decrease the speed overall. And we know that there's a finite end to how slow we can make molecules, because they can only get to 0 Kelvin. So what's going to happen is you're just going to shrink your curve, or the width of your curve, I suppose. I'm sure there's some sort of mathematical term that you would call that.
Smush.
Okay, we're going to smush our curve. And so it's going to move back this way, because overall our molecules are going to slow down, but it's going to cause it to get, you have to forgive me because I'm not going to make that curve the same, but just pretend like it was the same total mass or same total space underneath. But it's going to smush it together, and then that has to cause it to go a little bit higher, because you're going to have a greater number of molecules in that smaller space. Sound, is that what you're going for? Okay, fantastic. Right, do you guys want to call it a day?
And that's-
So everybody can go to class? Fantastic, thank you so much.